We knew we would have done better than the requirement, except for surprises. But the amazing thing was that we could understand the noise we were observing well enough to improve. And basically, despite the plan was do it a bit worse than needed in LISA because the test is going to be noisy, and then project to LISA, we're now where LISA has to be. So, we have skipped one phase, which is scratching our head on the noise and projecting the design on LISA. I think what we have demonstrated is a sensitivity that allows a great mission, a great observatory at low frequency.
Yeah, I mean, you were hoping to get within, I don't know, maybe 10 times, not quite as good as LISA. But you're there, and in some respects, you're better than that requirement as well.
Yeah, much better. I mean, we are better than what LISA requires, which is 10 times better than what LISA Pathfinder was required to achieve. Not at all frequencies, but in some frequencies, it doesn't matter very much. And so we have redesigned in the proposal we have done on LISA, we have reshaped the sensitivity curve, and the astrophysicists are so happy with that sensitivity curve because we have shown very low noise even at very low frequency. Here we are talking, up to now in my presentation I talk of hours. Now we're talking days, half a day, right? Our lowest frequency is half a day. And when you go to low frequency, you go to bigger and bigger sources, and you follow the source for longer and longer and longer, even years before the final merger.
So to be clear, what you've been doing, you've been looking at the accelerations, the movements in these blocks, and you needed to sense accelerations that were sort of in the femto-G range, yes? Yeah. You know, the millionth of a billionth. Less than a millionth of a billionth of the acceleration that an apple experiences on planet Earth. And you need to be able to see that and study it and maintain it over periods of hours, days even, because that's the time it takes for the gravitational waves that you seek are going to come through the LISA observatory.
Exactly. No variation over that time scale. However, this level of noise must be maintained then for years, because LISA is an observatory and has to observe per years, right? And I think observing LISA Pathfinder for many, many, many months was also very useful to understand if we can maintain these performances for a long period needed for an observatory.
And so while you were doing all of that, running LISA Pathfinder, you were also writing a submission to the European Space Agency to do LISA proper. And you submitted that, and we're on the path now, aren't we?
Definitely we are, right? We have flown a piece of hardware, so we know the system much better than you normally do with a new mission, right? Because we have a piece that we know, we have operated it, and so it's fundamental not to lose the momentum now and not to lose the knowledge. And that's why also ESA has accelerated the schedule, because originally the plan was to call the mission in 2019, and they have advanced the call by 2 years, basically.
So what's likely to happen now? We can't prejudge the Science Policy Committee of the European Space Agency, but what's likely to happen now as we move out over the next few years? Mm-hmm.
So there would be this study. It's called formulation, I think, in the jargon of space. So that you define which mission you want to implement. And then, as you were saying before, the next step is the so-called adoption. And when a mission is adopted, you start to spend the big money, right? So the next 3 years will be this formulation. And if I may say, let's move from there, right? Because it's always the technical progress that make the pace of a mission, right? So if LISA, as I am confident, will progress fast, then in 3 or 4 years, we could be in the situation where ESA has to decide if to adopt the mission, if the mission can fit in the long-term planning, our judgment is that LISA could progress so fast that could be launched in 29 or 30. That's the technical limit. Obviously, it's a prediction. Right? Where things have to progress technically, we could find showstoppers, but certainly we are a long way in the process thanks to this painful but successful LISA Pathfinder. So then we'll see. The next big milestone is to see the mission that comes out of these studies for the next 2 or 3 years. In parallel with the studies, ESA and the member state, but ESA certainly started, is investing in all the technologies that were not covered by LISA Pathfinder and have to do with the spacecraft-to-spacecraft interferometry at 5 million kilometers, right? That is not covered by LISA Pathfinder, which is a single satellite experiment.
Absolutely, because the separation between your test masses in Pathfinder was
38
centimeters, and
yes.
I think in the submission that you've made, you've gone for an arm length of about 2.5 million
yes.
kilometers,
yes.
haven't you? Although I don't think that's completely set yet.
No, that's not. That's certainly a matter of study. 2.5 million kilometer is in between the range that has been studied. So it was a prudent choice, makes a good mission. Then it depends on the study. The arm length may have an impact on cost, on mass, on things like that, and so it's certainly a parameter that has to be adjusted. The sensitivity at low frequency increases with the arm length, and so in principle, you would like to have the largest possible mission. However, you lose sensitivity at high frequency, so there is a technical optimum and there is a programmatic optimum because it could drive your price or cost. This will be studied, certainly in the task of the study.
And one of the things that needs to be sorted out as well is the participation of international partners, and the Americans were for a long time a key partner on the collaboration for LISA, and well, we certainly hope that they're going to be back in very shortly.
I would say that perspective, let me, an optimistic scientist, I think it's certain. And ESA and NASA are talking seriously since the beginning of the LISA Pathfinder news and the discovery. And the baseline for ESA is that to an L mission, an international partner should contribute not more than 20%. I don't think this is cast in stone, and also it's very difficult to understand 20% of what. So I think NASA will be a major partner of this mission. ESA will be in the lead, but NASA will be a major partner, and certainly the science community worldwide is a united community that sees this as a global effort where the American and the European will collaborate very strictly.
We've seen with LIGO these mergers of black holes, albeit reasonably sized, in the sort of 10, 20 solar masses. What will we get from LISA? What will it enable us to do that, say, LIGO cannot?
Well, many things. It's a different physics. First, there are two things. Low frequency means big. Right, it's Kepler. When things are far apart, they rotate slowly, right, or they move slowly. And so big means either sources with the mass of millions times of the sun, even billion times of the sun, and this monster exists and are in the center of galaxies. And so now when two galaxies collide, right, now it's not two black holes colliding, it's two galaxies colliding with a black hole. And as I was saying at the briefing, this signal is so intense. The signal-to-noise ratio is thousands at the edge of the universe, where they can possibly exist. They cannot exist before recombination, right? But whatever, and we see older and older and older galaxies optically. So whenever they are, wherever they are, they will be detectable by LISA. And also another fantastic source, if that these big guys swallow small guys, and the small guy falling into the big guy send gravitational waves that map the event horizon around the central black hole. And this is a fantastic general relativity laboratory with a high signal-to-noise ratio down to the very detail of physics. But also low frequency means big may mean two small objects very far apart. So a few months after LIGO detected its binary, there was a flourishing of paper showing that LISA been in orbit, they would have detected the system a year before the merger. And that's fantastic. You detect it a year before, you follow through, then you lose it for a week, and then it reappears in LIGO. I mean, I'm not an astrophysicist, but think what you can do with these things. So.
And seeing those monster mergers from way back, I mean, that essentially allows you to trace the evolution of the cosmos, to see the development of structure from the earliest times right through to the present.
Yeah, well, I mean, if, as people think, galaxies form by mergers, so two small galaxies merge and form a bigger galaxy, because these galaxies, this merger, sooner or later enter in the frequency band of LISA, because they spin faster and faster and faster, and so at some point, and so if you look at the sky with LISA, you have a sort of cosmic stratigraphy, right, where you see smaller galaxies in the past forming, bigger galaxy, and I know that they have very strong appetites on tracing back the formation of the galaxies we know and the universe we know through following this natural history of galaxy formation through mergers of black holes, 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 of black holes.